right. We're going to talk about the new topic, and here this is a special application by using double integral. So here we put it at the end of the this chapter instead of a later discussion as arranged in the textbook, I think. Well, so now we want to introduce this idea first. And I think we all notice that the discussion of all this triple integral, double integral, and their applications are related to some geometric interpretation. In many cases, if you have the ability to visualize the object, it will be really, really helpful. And for example, let's look at this. So suppose we have this U and V plane, and there is a region D we can pick the pair value U and V from. And then if we have this so-called the vector valued function, which depend on the parameter, okay, so what we should think of is all the x, y, z component of this vector R will be a function of this parameters u and v. Okay, remember these R is so-called the position vector, and the tip or the head of the arrows or vectors are actually a point in space over here. So now you can see we are establishing the connection between a parameter pair UV to a point in three-dimensional space XYZ through this R. All right. So this is so-called the parameterization. So this is so-called the parameterization. Parameterization of S the surface. So this is a general description of our procedure, and we can think about some specific example. For example, we all know the sphere for radius 1 and is centered at the origin is going to be described by this equation xy about xyz in the Cartesian coordinates, right? So what we mean is any point x, y, z on the sphere have that relationship x squared plus y squared plus z squared equals 1. Okay, and here remember, if we're thinking about the spherical coordinates, we noticed. So this means rho, which is square root of x squared plus y squared plus z squared, is going to be 1. Okay, and then by using the spherical coordinate, we remember, recall the 0, recall in spherical coordinates, rho equals square root of x squared plus y squared plus z squared, and x is what? X is rho times sine phi cosine theta. Y is rho times sine phi sine theta, and z is rho times cosine phi. If you remember the conversion between Cartesian and the spherical coordinates. Now, for this particular sphere, we already know rho equals 1. So rho, rho is going to have a fixed value. So now we see to represent any point x, y, z on this sphere, we can use this spherical coordinates, and the representation we get will depend on the azimuthal angle phi and polar angle theta, azimuthal angle phi and azimuthal angle phi and polar angle theta. So by using two parameters, phi and theta, we can represent all the points x, y, z on the sphere. Okay, so if we write it in the vector form by phi and theta, this is sine phi cosine theta, sine phi sine theta, and cosine phi. So this is indeed the parameterization of this sphere for radius 1 centered at 0, 0. And obviously we have the restriction on the choice of the theta and the phi. Theta is between 0 and 2 pi, phi is between 0 and pi. Okay, so this is the one of the examples for the parameterization of this surface that we are familiar with. All right, so in general, and now let's look at this in general description. So x depend on two parameters, y depend on two parameters, z depend on two parameters. And we can always write it in the form r of uv, which I think we wrote it earlier above. Let's just summarize. And for here, u and v is going to be chosen from a plane UV and within a domain D. Okay, so then if this is what we have, or this is an equivalent form, then we would say a parametric surface S given in one is called the parametric equation of the surface. All right, so in some case, we can write this R vector, the parameterization. So we call this R, we call this R the parameterization of the surface. Right, so the R could be written in this, not in the component form, but with the special unit vector, IJK form. And if we sometimes, well, in most of the cases, I think, we're going to write this in this particular row format of the component form. Like this. All right, so now we are going to use this parameterization. We're going to use this parameterization to discuss some geometric quantity that we need to really remember and know how to use. So here, let's just talk about it. Remember, the vector function that represents the plane has the point P with a position vector R naught, and that contain two parallel vectors A and B. Could be written down very easily. You guys remember, right? Well, let's draw a diagram. Suppose this screen is what we have for the plane, right? So this point is indeed P naught, and then the two vectors A and B is formulated so that we put their tail at the same point P naught and point to A and B direction on their own. Okay, so here we can see for any point inside of this plane spanned by those two vector A and B could be obtained by doing this. All right, which has here, this is a parameter U. All right, and then what? And then we have this parameter v. So we scale this vector a and a vector b, then add them together. Then we get this arbitrary point p inside of this plane. So in terms of the vector calculation, we would know the plane, the point, this parameterization of p could be obtained by doing this, which means this u scalar type. Well, I guess I have some difficulty. So this should be what we have for the representation of this plane. I mean any point on the plane. Okay, so this is the one example, and how about the others? Well, we want to represent the elliptic paraboloid. This one. This is supposed to be a surface in space. This is a quadratic surface we discussed. So how about we use a vector parameterization to represent it that is consistent with the notation that we introduced in this form? Well, obviously, we do have to have two parameters. One could be chosen as x, the other could be chosen as y. So this parameterization will be like that. X and y will be themselves, but the z will be depending on x and y. So the parameterization, if you write it in the component form, which will become x squared plus 2y squared. Okay, so for this so-called the graph function, depending on x and y, we can always write the parameterization in this way. Oh, by the way, the two parameters in the previous example we discussed is u and v here, right? Which is OP naught plus u a plus b, depending on this a and b vectors that it's given. And after this AB vector given here, they are fixed, and the only free parameter we can change will be u and v here. Okay, so there are other surfaces you can represent in this way. For example, we can think about the surface that is generated by rotating a function given here. So, well, let's look at it. If we have, this is the x, this is the y, and this is supposed to be z. So if we have a curve, this is the y equals f of x. And what we need to do here is that, well, this is a, this is the b. What we need to do here is rotate this curve, y equals f of x, around this x-axis. Essentially, we do get something like this. So this is obtained by rotation, right? So how do we parameterize this surface of rotation? which is obtained um, by rotating this y equals f of x? Well, here, what we can think of is that for any point on this surface, x could be as served as a parameter, all right? And then we can see if we jump on top of this x-axis, we look down, what do you have? We'll have a circle. That circle will have the radius of f of x. So, so look from right side, we'll see a circle of radius f of x. All right, and then we would know this y and z. So this is indeed, if we jump on top of the x-axis and look down, we will only see, I guess, we will see this is a y, this is a z, right? So y and z could be represented by using this polar representation, which is f of x times, depending on how you arrange this. So the parameterization for this surface revolution in parametric form is this. We can write it down in vector form. So x and theta, which is x is x, y is f of x times cosine theta, and z is f of x times sine theta. All right, so those are the interesting and the useful representation of this parameterization. And those are the example we can go over, but the key understanding of this is that we always just try to parameterize each of the component x, y, z on the surface by using two parameters. In some case, those two parameters are just u and v arbitrary constant. In some case, like this, we can see the two parameters could be x and y themselves, and which form you need to use depend on the problem, and we have to analyze them case by case. All right.